is bigger than or equal to 3, we have this conformal Laplace operator, which in my notation is the Laplace Beltrami and plus a constant, and then there is the scalar curvature of G. And this Cn is a very specific constant, n times n minus 1. And then when n equal to 2, this second order Laplace operator becomes Laplace operator. And the PDE related to this conformal Laplace is Laplace GU is equal to this dimension constant times RG hat of U to the n plus 2 over n minus 2 power, where G hat is U to the 4 to the n minus 2 G. So this is an equation of prescribing scalar curvature when n is bigger than or equal to 3. And when n equal to 2, the same equation becomes Laplace GW plus Gaussian curvature equal to kg hat e to the 2w, and now the g hat now is e to the 2w times g. So that's the second order PDE. And the most important property of LG is conformal covariant property, which Paul also has talked about. So in this notation, this means that this L of G hat operating on any function phi is U to the minus n plus 2 over n minus 2 power times LG of U phi for all function phi, say in C continuous or C infinity on the manifold. The conformal covariant property. And when n equal to 2, so this is again for n bigger than or equal to 3, and for n equal to 2, Laplace operator has the property that when you look at Laplace for G hat, this is e to the minus 2w Laplace for G. Yeah, so this is a property for G. So I never really defined Laplace G. Laplace G is the Laplace Beltrami operator. So this is defined to be the determinant of G square root, and then in local notation is di, and then G upper ij, and then dj, and there is a square root of G there. Square root of G. In local notation. So this is the Laplace Beltrami operator. So this equation is the prescribing Gaussian curvature equation. And today I will begin to talk about the class of generalization of the second operator to higher order operator. Okay. So the story began in 1983, and the first example is an example by Pennines. And sometimes we call this class of operator Pennines operator. So in a study of Maxwell equations, Pennines look at this conformal covariant operator and wonder if there is generalization. And then what he does is he has this fourth order operator in n dimension. So this is an n-dimension fourth order operator, and this operator, he just write it down. And the leading order term is Laplace squared. So it's a bi-Laplace operator. And then on general manifold, there are correction terms. The correction terms are second order, which is, I just want to write it down for later reference. There's this divergence. And then there is this constant an, scalar curvature of G, and then the metric G, this is plus some constant times the Ricci curvature of the metric G, and then divergence term. So this is a divergence gradient. So divergence and gradient together with Laplace, and then the coefficient is involving scalar curvature, and then the Ricci curvature of the metric. And then in n equal, then there's n minus 4 over 2, and then what he called is Q4 n term. Yeah, a Q4 n term. This Q4 n term one can also write down, but later on I will write down when n equal to 4, what happens. And this operator is defined when n is actually Pennice define it for n bigger than equal to 4, bigger than 4. Okay. But and then an, bn are coefficient, and it has the property if we write g hat equal to u to the 4, n minus 4 over 2 times g. Then this P4n also has the conformal covariant property, like the conformal Laplace on g hat operating on function phi. Now it's u to the n plus 4 over n minus 4 of P4n, and then g operating on the function u times phi for all phi. Very similar to the conformal Laplace operator, but it is P4n. And then it also prescribes Q4, because then P4n operating on the function 1 is n minus 4 over 2 times Q4n. Operating on the function 1 is this Q4 n's operator on the metric G. I mean n minus 4 over 2. And this is defined for all n bigger than equal to 5, for all n not equal to 4. And so he just pointed out there's this class operator, and then he write down what is Q4n because it's computable. He write down explicitly. And this is usually called a Pennice operator. But Bronson looked at this class of operator, and then he said that from conformal Laplace operator, this second order elliptic equation of prescribing Gaussian curvature, there is a process which I briefly described yesterday, let n tends to 2. And then you get a Gaussian curvature equation. So his point of view is, although this Q4n has n minus 4 over 2 there, and when n equal to 4, you look at this operator P44, you are not going to see Q44. But on the other hand, from this PDE, this fourth order PDE, biharmonic, the Laplace operator, this type of PDE, we can derive another fourth order PDE defined on 4 manifold and find out what is Q44. Okay? And that's what Bronson did. So nowadays, in the case when n equal to 4, this Q curvature is called Bronson's Q curvature. Okay. So Bronson's Q curvature. Okay. And this Q in particular case, let me write down Q44. So in particular, without ambiguity, I just write Q4, defined to be Q4. And he write it down. So Pennice write down Q4n, and he let n tends to 4, and then one get is a following expression. 112 minus Laplace R and plus scalar curvature square minus 3 times the norm of the Ricci curvature square. That's a curvature operator, and which involving Ricci tensor. And then for this operator, one also have this P4, this P44. Okay. And for the record, let me write it down. This is minus Laplace square plus the divergence 2/3 scalar curvature G minus 2 Ricci curvature G, and then times the gradient. Okay, so P4. And then he pointed out the relation before P4 to Q4 satisfy a relation very similar to the prescribing Gaussian curvature. Okay, so P4 operator operating on W, on G, and in his original 112 notation, there's 1, 2 there, is equal to 2Q of G hat of e to the 4W. Okay. And this is for G hat, which is e to WG. Okay. And now there is also P4, so the now one can draw a parallel program between n equal to 2 and n equal to 4. N equal to 2, we have the Laplace operator, and which has the property Laplace G hat is e to the minus 2W Laplace G. And for fourth order operator, this operator also has the property, when we look at G hat, this just take out the conformal factor Pg. Very nice conformal covariant property. Just take out the conformal factor. And then we have the Gaussian curvature equation that I have already write down. Laplace GW plus Kg is equal to Kg hat e to W. And then we have this corresponding P4 equation. And at this moment, everything is formal. But we also know that in 2 dimensions, Gaussian curvature is a very important operator. And in particular, there is a Gauss-Bonnet formula. And Gauss-Bonnet formula has 2 pi. Euler characteristic is equal to this the Gaussian curvature dVg. And Brunson noticed that this Q, again, is related to Gauss-Bonnet on 4 manifold. It turns out 8 pi Euler characteristic of closed manifold without boundary. So if this is closed without boundary, then there is this integration of Qg dVg there in the Gauss, the Felting thing, but then there is also the term. Notice that this P4, this Q, is related to an operator which is conformally covariant. So that means it will not detach those terms, which is a pointwise conformal invariant. And that turns out to be the term which is equal to 1/4 of Weyl curvature square dVg. So this is on these 4 manifold ends. This is the Weyl. And it turns out that on 4 manifold, this Weyl curvature is a pointwise conformal invariant. That is, Weyl of G hat turns out to be equal to exponential minus 2W Weyl for the G metric. So this is Weyl. Pointwise invariant. And so for 4 manifold, since this dV volume hat G hat is E4W dVg, so that means for these 2 tensor or tensor, so Weyl G square dVg is pointwise the same as Weyl G hat square dVg hat. So the conclusion I want to make is, hence, the most important property of the Q curvature is Q curvature in itself does not have pointwise invariant, conformal invariant property, But since due to Gauss-Bonnet, the left-hand side is a topological quantity, and the first term is a pointwise conformal invariant, the conclusion is integration qg dvg is a conformal invariant. So this is an example of integral conformal invariant. So, and now there is a lot of study of this invariant property, and say, let me begin by some simple cases. So note that on plane domain, or on plane domain, on flat domain with Euclidean metric, this P4 operator is nothing but a bi-Laplace operator. Okay. And in the flat case, of course, Q is identical to 0 for dx metric. And another typical example is on M4, if this is an Einstein manifold. So that means the reci of G is equal to lambda times G in my example. Reci G in this case. In this case, this P4 operator turns out to be conformal Laplace operator composite with Laplace operator. Conformal Laplace operator composite with Laplace operator. Okay, my conformal Laplace is minus Laplace, so I composite with minus Laplace. So P4 is just conformal Laplace composite with Laplace operator. So in today's lecture and tomorrow's lecture, I'm going to try to convince you that besides this formal analog, there is indeed a geometrical content of the Q curvature. Okay. And the Q curvature, in some sense, modular the pointwise conformal invariant part. The vial curvature usually measure how flat is the manifold. So on Euclidean space or on sphere, vial vanishes. And modular this flat part, Q curvature gives information about geometry. And so today, I will cover some start with the case of things happening in plane domain and try to say that even in that case, Q curvature gives us some information about the geometry. So here is the theorem I want to cover. So on domain R4, say R4.
Integral conformal invariant.
Yes. Yeah. So on R4, suppose I begin to consider a metric dw dx squared. Okay. And then the relation is now minus Laplace square of w now is my 2q for this metric G. So this is my metric G. Or if we want, we can call it G hat and then E for W. So that's on flat domain because Penny's operator is just by Laplace on R4. And now let me say that in this case, there is some geometric inequality involving Q curvature. So to do that, first let me recall some classical result. Or R2 E2 W dx squared. Some classical result. Okay. So one classical result is the following. It's something called Conformal inequality. Which says that on M2G, suppose I'm having a non-compact complete manifold. Or you think about R2 E2W dx squared, but with a complete metric. And then the result says if the Gaussian curvature dVg is in L1, it's integrable, then we have the Gaussian curvature Kg dVg is actually less than equal to 2 pi times Euler characteristic of the manifold. Okay. So there is a growth of the Gaussian curvature. And furthermore, there is the result of Huber later generalized this Gaussian inequality. They say that in this case, you can compactify the manifold. So the manifold is this and with holes. And then one can compactify the manifold. So in this case, M2 can be compactified with finite many M. Each M is conformally the same, equivalent to R2 subtract some ball, some compact set, omega I compact. Okay, and then one can tell the difference between 2 pi Euler characteristic subtract the Kg dVg describing the behavior of the metric near M. Okay, and in this case, chi M minus.
So the ends are really points.
Yeah, these are points. Adding finite many points. Yeah. So. Yeah, finite many points. Should I say points or something like that?
Punctures.
Yeah, punctual points. Punctuals. Subtract points there. Finite many points. So P1 up to Pk. And each omega I is a neighborhood, removing those points. And then let me write this down. The difference of this, of KdV integration. Okay. So in this case, I look at the difference. Difference of them is sum of mu I from 1 to k. And each mu I is the asymptotic behavior of the isoperimetric constant of the behavior of the metric near those ends. Okay. So each mu I is equal to limit of distance on, so there is this point, and then pi, and then you look at ball radius r, and you look at the length of the r, and then there is this omega I. Okay. So here you should look at the 4 pi of area of r, and that think about r go to 0 or go to infinity, and this is AR is equal to area of ball of radius r subtract omega I. Yeah. So the r, so omega I is here. You look at larger and larger ball. Outside the ball, you look at the isoperimetric inequality of L over A, and that's mu I near pi. Okay, so this is the classical inequality. The only point I want to make is note that VI is positive if this integration of 1 over 2 pi k dv is strictly less than, if it's less than pi n. Okay. So if you are going to bound the L square bounded by certain A, the isoperimetric inequality holds near the infinity end. Think about this as points in infinity. That happens if the Gaussian curvature is strictly less than 2 pi Euler characteristic. Yeah. So that's the classical inequality. Hope I have stated it correctly. Okay. And now, in contrast with that, near each endpoint. Okay. So in contrast with that, let me say that there is this result. First, let's try to say this result has a 4-dimensional analog and with Gaussian curvature replaced by Q curvature. So here is the theorem. And this is a result of myself with Qingjie and Paul. And in a Duke journal around 2000. And then there's a follow-up work in the invention in around 2002 or something. And this theorem I'm going to state is on R4 case. So an easy case is the following. It says that on this situation, R4 dg2w dx squared. So we look at a special 4 manifold. Suppose it's complete metric on R4. Okay. And if Q curvature, Q is defined to be the metric which satisfies this PDE. So treat this as definition of Q. So QG is this biharmonic operator is Laplace square W, and then its QG is defined this way. And so if QG is integrable, so this is the DVG metric. So if Q is integrable in its own metric, then we have an analog of this result. In this case, there is one n. Okay. So then we want to say, and if there is an additional assumption, if the metric is normal, I'm going to explain what that means. I'm going to explain this additional assumption. It's normal. And then we have the following thing. First, this Q G dVg now is less than equal to 4 pi square times the Euler characteristic of R4. And in this case, this is equal to 1, so it's equal to 4 pi square. Okay. So we have a bound of QG dVg. So in this case, let me say, recall that on S4, if one write down the canonical metric integration of QGC dVGC, in this case, is equal to A pi squared. So we have 1/2 of the A pi squared. So it's like in this case, the Gauss-Bonnet is 4 pi Euler characteristic, but K is integrable, then you reach 1/2 of the characteristic. So that's this analog. And then we can describe, in this case, it's R4, there is only one point at infinity, and so one can describe the end behavior of 4 pi square of integration QG dVg. The difference of 4 pi square to this term is again the isoperimetric constant of the metric at infinity. So its limit r tends to infinity of the boundary of the ball to the power 4/3 power and divided by 4 times 2 pi squared 1/3, and then the volume of the Euclidean ball. Okay. So this constant is just a normalization constant. So it's a similar analog of this Huber theorem in the special case when the metric is a conformal metric to the Euclidean metric, and the important condition is Q is integrable. Okay. And now we also add a condition G is normal. So now let me say what does normal mean. So normal means the following thing. So here by normal, our definition of normal means the following thing. We say that if we look at the bi-Laplace operator on R4, the Green's function, this is a fourth order operator on dimension 4. So the Green's function is always log. The Green's function is log. Is the Green's function. So any function which satisfies Laplace square W equal to 2Q E4W, you may recapture this function through its Green's function, but on the other hand, there is a modular kernel. Okay. So we say that it is normal if the modular the kernel pi is not there. So that means if W of x, this satisfied is equal to 1/4 pi square times integration over R4, and now the Green's function 1/x minus y, and we normalize it by y, absolute value y, and now there's this Q of E4W of y, and then dy and plus. Maybe I add 2Q here. Then it should be 1/8 pi square. So sometimes this 2Q is this 2Q. And then plus the constant. Okay, this is for all x in R4. Okay. So what does that mean? Okay. That means that suppose we define this to be equal to U of x. Then this U of x definitely satisfies Laplace U equal to 2Q E4W. E4U. E4W. Okay, this is E4W because it's the reproducing kernel for the Green's function. Okay. So what we say is normal if this U and the W differ by a biharmonic function, and that biharmonic function is a constant. Okay. So we say it's normal. Normal means W differ by H with double Laplace H equal to 0 and H a constant. This double H is definitely different by this representation formula by a constant. And this seems to be an artificial condition. But on the other hand, it turns out there is a natural geometrical property which implies this property. So the first lemma is that it turns out that lemma 1 is that it turns out if the scalar curvature of the metric is greater than equal to 0 near infinity, implies the metric G is normal. So what we are saying is this Q curvature is relating by definition of Q. If we remember Q, this Q is equal to Laplace R and then plus some term. So it's a fourth order curvature term. Fourth order differentiated metric 4 times. So, and then to get good control of the metric, you need to have some constraint on its second order behavior. And what we are saying here is, if this second order thing at infinity is positive, then the metric already has some constraint on its growth, and it's normal. Okay. So that's the lemma. So I'm going to say a little bit about this lemma, proof of this lemma now. Okay. So let me first prove this lemma, and then I will begin to sketch the proof of this theorem. So proof of this lemma. And so again, we will show Laplace H equal to 0 imply plus the scalar curvature is positive near infinity, imply H is a constant. This H is the difference of W to this Green's function representation. Okay, so look at this, we will show. Okay, so in this case, the proof actually is very easy and follow the strategy of what we think it is. But let me go through that. Okay. So to see that, first, we know that the metric is E2W dx squared. So let's write down the scalar curvature equation. And that's the second order elliptic equation. So, but we use E2W to write it, and it turns out the equation is scalar curvature, this R is equal to RG times exponential 2W is equal to Laplace W plus gradient W squared. Okay. And so if this scalar curvature is positive, and we have this negative term times negative term, so scalar curvature is positive would imply Laplace W is negative. Okay. But this is all near infinity. We only care what happened near infinity. So Laplace W has a sign. And that already tells you a lot, because then this double Laplace H equal to 0 implies that Laplace H is a harmonic function. So we first set out to show that this harmonic function has a bound. So look at this harmonic function Laplace H at x naught. This will be equal to its average over the sphere of Laplace H of x dx. This is, say, near x naught near infinity, averaging. So you begin to write down Laplace H in terms of Laplace H in terms of Laplace W minus Laplace U. This U is this function. Define this function to be U. So I call this, define this function to be U. Okay, so now we have two parts. One part is the Laplace W part, the other part is the Laplace U part. I'm sorry, maybe I will use, in my note, I have the other way around. Laplace W. Okay, sure, that's fine. Okay, so there's a Laplace W. Laplace W is equal to, so I write down Laplace W. This will be equal to the averaging over the sphere, and now there's a minus Laplace W. Laplace W, sorry, just Laplace W. And then minus Laplace B. Okay. And now this Laplace W, as I say, has a sign. Where x naught is near infinity and this ball is very close to x naught, this is negative. Okay, this is negative. And now this function u satisfies this equation. So Laplace of u can be directly estimated. Okay. And so here we use this property, this function is in L1. Okay. So when you estimate Laplace u is an estimate of the Green's function of differentiate log. When you differentiate log once, well, you have 1 over distance. Twice, you have 1 over distance squared. So in this case, you are going to have this Laplace u would satisfy the property is less than equal to 1 over r squared, and then up to a constant times this integration q e to 4w, which is integrable. Okay. So the point we are going to use is this tends to 0 as r tends to infinity. So from here, the conclusion is now we have Laplace hx naught is less than equal to 0. Okay. And Laplace h is a biharmonic function, so if it has a sign, Liouville theorem tells you it's a constant. Okay. So by Liouville theorem, imply Laplace h is a constant. And so, from there, we are going to deduce h is a constant and then follow from the same strategy, because this Laplace h equal to 0 implies Laplace differentiate with respect to xi is 0. And now you are going to show that this would imply, using the, again, same strategy, and using the fact that the scalar curvature is positive, you are going to get a bound of hxi. And from there, you are going to show that this hxi is a constant. And from there, we conclude h is a constant. That finishes the proof. Okay. So this is so the only point I want to say is that since this harmonic function, the Laplace w has a sign which has strong implication on the behavior at infinity. So so this theorem, we have this normal condition, but at least we know that when the scalar curvature is positive, the metric is normal. And the remark is that it turns out that normal is a necessary condition for this theorem. Okay? Normal is necessary. For theorem, for the theorem. And because one can easily add a function of the type x squared, this is 0. If it's not normal, then you can add function like that and still satisfy the same PDE. And you can make a metric which is complete. Say you take a Euclidean metric, which is the metric, choose V, such that this V is the usual standard metric on S4. And then your W is equal to somehow V plus X squared. One can see this type of result doesn't hold. This is not normal, and then the isoperimetric inequality, the result is not hold. Okay. So normal is somehow a normal condition which is quite natural. And then the second thing I want to remark is in n equal to 2, it turns out Huber's result is really to say that when Gaussian curvature is in L1, the metric is normal. With no constraint, Gaussian curvature is in L1, then the metric is normal. So in 4 dimensions, we add some condition to force it to be normal. Now, I'm going to sketch the idea of the proof of this theorem. By the way, this Conformal and Huber theorem, there are many different proofs, but the original proof result in complex analysis, actually using Picard theorem. It's quite sophisticated. And the proof we are given here follows from a modification of Robert Finn on reproof of Huber theorem. Okay, so the idea of a proof of this theorem this R4 theorem is the following. Okay, so and obviously, if we want to prove or resolve this type, 1 minus 4 pi of Qg on R4 and near its n behavior, what we are going to do is we are going to exhaust R4 by compact region. Okay, by compact region. So that means that you are going to apply a Gauss-Bonnet formula for domain with boundary, not just R4. You exhaust it by boundary. So that means we should take a look at the Gauss-Bonnet formula for manifold with boundary. Okay. So if M4 is closed, then without boundary, I have already this Gauss-Bonnet theorem, which is equal to Weyl square plus Q. Forget about the constant here. Here is 1 minus 4 or something. Q curvature. Q curvature. And then on Gauss-Bonnet, if M4 is with boundary, we also have a Gauss-Bonnet theorem. Let's take a close look at the Gauss-Bonnet theorem. And in that case, we have this Gauss-Bonnet formula with boundary, and there is still this interior term, Weyl square, and plus Q curvature on M4. But then there is also the boundary term. So I should say in two-dimensional case, this is 4-dimensional. In two-dimensional case, you have 2 pi Euler characteristic with Gaussian curvature plus geodesic curvature, totally geodesic curvature on the boundary. Okay, so this is for two surfaces with boundary. So on 4 manifold, there is also the curvature. So one look at Gauss-Bonnet integral for manifold with boundary, and for our purpose, we begin to think you examine the Felfin term. Okay. And here I like to put a remark. Our Q curvature has 2 components. One is the 4th order term, and one is this quadratic curvature term. There's a minus 1/12 and minus r plus this quadratic curvature term. If one looked at the original Gauss-Bonnet formula, the way Chang derived it, this Laplace R part does not appear. Okay? And indeed, on closed manifold without boundary, this Laplace R always integrates to 0. Okay? So there's no reason to write something whose integration is always equal to 0. But the magic in what happens is, if you add this term, which is integration, the totally divergence term, the integration is equal to 0, then this Q is associated with this linear operator. Okay, so make it easier to study not an original Felfin term, but this term. Okay, so that's the magic. And so if we look at the Gauss-Bonnet formula with boundary, in the original Gauss-Bonnet integral, you have term. But since here you add an artificial term of Laplace R, that suggests when you write this other boundary term, you should seek some expression of this term which may have a divergence-free term, but which is naturally related to to some conformal covariant operator. So this work was done by Bronson and Peter Gilkey, and also redone by Qingjie and Marshall in the late 1980s. We begin to rewrite this Gauss-Bonnet formula. To make the long story short, we find it's most natural to write the boundary term into two terms. One is we call T2 term. One is this Q is a Q4, and this T is a third order boundary term. And this L, I don't need to write down this L and T. The expression in general is complicated, but on the other hand, this L, in a special case of totally geodesic boundary, one can write down easily. In general, the expression is more complicated, but if the second fundamental form is not a totally geodesic boundary, then in that case, the T term can be written down as 1/12 of this scalar curvature d normal. A simple expression like this. So the strategy is really this Laplace R term. When you integrate it to boundary, it's dr d normal, and that cancels out with this T term. Okay, and the L term is a pointwise conformal invariant. One can write down, but we don't need to. So it's a pointwise conformal invariant, like the vial part. But what's the advantage of this T? This T is related to some third order operator which has the same conformal covariant property like the Penney's operator. So there is an operator P3. P is associated with a P3 operator. And this P3 operator, again, in general, the expression is complicated, but in the case of totally geodesic boundary, is the first order term is Laplace and take normal derivative. So it's a third order term, but it's a dd normal of Laplace and plus Laplace theta of dd normal. So this Laplace theta is a boundary Laplace. And then minus a lower order term. I don't need to write it down. One can write down. Okay. So, and it turns out this P3 operator has the property that is describing T3 plus T3 is equal to T3 of G hat E3W. So this is on the boundary of the manifold, 3 manifold. Okay. One can relate this T3 to some operator P3, and one can write it down. Okay, so at least look a complicated schedule, but it does mean that in the R4 case, where this vial part and L part all vanishes, the term we should pay attention to is Q4 and T3, okay, in this case. So that motivates the following study. So the proof of this theorem now has 2 parts. So the proof of this theorem is step 1 is we look at the case where W is a radial symmetric function curve. First, if this conformal factor is this, and then we have an ODE. Okay. So in this case, if we write x equal to r, and it turns out it's easier if we look at things in cylindrical coordinate. We write it in exponential t, defined by that. Then the ODE of this Q curvature equation takes the following form. It's ddt squared minus 2 ddt, and then this d squared dt squared plus 2 times ddt, and then times w plus t. Now is equal to 2q of e to w plus t. So that's the ODE. Okay. Using this coordinate, I just write it down. So that suggests one should look at this function v defined to be w plus t. So this is my v, which satisfies this fourth order ODE. Okay. And now, in terms of this v, is one begin to look at its behavior near infinity, and we are aiming to prove a relation like b, this integration q, integration and 1, and look at that. And which, in this simple situation, let's look at the Gauss-Bonnet formula. Okay. So in this particular case, so the Euler characteristic is 4 pi squared. And then this is written now into two terms. One is Q4 term, one is T3 term. And the Q4 term is integration of, say, s less than equal to t of QE4V. Now I use the t coordinate, s less than t. And then there is a boundary term. So this subtracts that. Now it's the boundary term, pro t of e to the 3v of s equal to t term, because that's the boundary term. But on the other hand, we can easily compute this t, because in that case, we know P3. Okay? So in that case, t of e to the 3v is just equal to P3 of v in this case, and then it's ODE, so one can compute it in terms of its third derivative plus first derivative. So it's an ODE equation. One write it down. So, and now what we are having is that you can now write an asymptotic behavior of V because it satisfies that ODE. So it's an ODE analysis, and I will not go into detail. And it's a routine argument. And what we have is the following. So what we get is that you can write down this V of t now is equal to C0 plus C1t and plus C2 exponential minus 2t plus C3 exponential 2t plus a function f of t. Okay, and well, one has a limit. One can show that when Rg is positive, would imply C3 is 0. One use that to compute. And C2 is 0. And C1 is 1 minus 1/8, and then minus infinity to infinity of this 2q E4B of dt. So use this fourth order ODE and this PDE, one can see that. And the only thing one to see, the all behavior is information is contained in this C1, and C1 is now limit of t tends to infinity of v prime t. Okay, and now one can, now this v prime of t is equal to this because of this asymptotic behavior, and one can begin to compare that to the volume form of v, and the area form of V. So if V4 is defined to be equal to volume of the region S less than equal to T of S3 and then integration minus T to T of E4V, that term, and so that corresponds to the volume, and V3 is equal to 1/4 of the surface area S equal to T to the 3V, then this V prime T can be computed to have comparison to V3 to the power like what you want, and then there's this constant times V4. Okay. So for ODE, one just write down what is ODE, and the reason one consider this would think in this way and think about why this T can be computed using the derivative of V is motivated by our geometrical understanding of what the boundary behavior should be. Okay. So that's the ODE. So that's the first step. And then the second step of this thing is forcing the thing to be radial symmetric. So step 2 of the proof is showing that G is normal implies W is almost radial. Okay. So what does that mean? That means that one can show that W, if one defines W bar of R to be the averaging over sphere of boundary R of Wx, and then D surface measure, D sigma of X, surface measure on ball. So, and then what you show is this ODE, this G normal, this expression would imply that you have the integration of boundary ball of radius R e to the kw d sigma is equal to ek of W mean value at the point R, and then e to the little o1 for all k. A pure analysis, just using this expression of this GW in terms of its integration, and using the fact that this Q is integrable. So that means it's almost like a radial function in that sense. Okay? And using this, one can compute the area at infinity and follow the strategy like step 1. Okay? So I don't go into details here. Okay? So that's the proof. And now, so that's this theorem. Okay? But this theorem only says that if this Q is integrable, then the behavior at infinity is fully controlled. And if this Q is small, it's less than 4 pi, then you have the length is bounded by the volume. So if this is positive, the volume is bounded by the length. Okay? Isoperimetric inequality holds at infinity. And turns out there is much more to this strategy. Okay? So let me state a second theorem, which is a more recent result in last year. And for that, let me recall another classical result. Okay? So a classical result, so in two surfaces. On two surfaces. It turns out there is this classical result of Fiala, Huber. And this is 41 and this is 57. Okay. So what they say is that in this case, one can talk about the isoperimetric constant on these surfaces using the size of its Gaussian curvature. It says that omega g, say omega is containing N2, okay, is less than equal L square, greater than equal to 4 pi a usually on the plane domain. So we are talking about omega g is the volume and bounded by length square. And this theorem says that one knows that constant, and that constant is controlled by the size of its Gaussian curvature. So the constant is 2 times 2 pi minus the positive part of integration of k plus of m. Okay. So this constant is the positive part of the Gaussian curvature and then integration over the surface. So on plane domain, this Gaussian curvature is 0. So one gets a constant 4 pi. Okay. And so this constant is finite. This constant is finite if this integration of Gaussian curvature is strictly less than 2 pi. Okay. So there is isoperimetric constant on this domain and area if Gaussian curvature is less than 2 pi. The positive part is less than 2 pi. And one knows this is the best. Note that integration of Gaussian curvature equal to 2 pi, then the result fails. Intuitively, it's the following thing. One can consider a cigar region. Okay? So the Gaussian curvature equal to 2 pi is the Gaussian curvature of a half sphere, half circle. So if one have a long tube, and if the Gaussian curvature is exactly 2 pi, and if you cheat it a little bit, make the Gaussian curvature flat, then this L square is this length, while the surface area can be as large as you want for a long cylinder. So there is no isoperimetric constant. So that means this k plus less than 2 pi is crucial for the isoperimetric inequality hold for these surfaces. And it turns out, surprisingly, there is a result of this type also for Q curvature. So, and this is recent work of E1. And this is 2012 and maybe 13. It's on the archive. One can find the archive result on Q on archive, posted on archive. So her theorem says the following thing. It says that on Rn and E2W dx, and suppose this is the metric G, and suppose this is a complete metric. And suppose its Q curvature is integrable. And suppose G is normal. Okay. And then in this case, one can consider this Laplace n over 2. When n is odd, one can also justify this as a pseudo-differential operator. But let's pretend n is even, and then this W, and then there is this generalization of QNN curvature e to the NW. Turns out this Bronson's notion of Q curvature can be generalized in n dimension for n even. Okay. And so there is this QNN, one can define it to be this way. So the result, G normal, is the same as saying that you can represent this W in terms of its Green's function expression of this Q curvature. And suppose this Q is in L1. Okay. And then what the result says is there exists a sharp constant Cn. And that sharp constant is exactly the 1/2 of this Qnn on the sphere, integration on sphere, on the standard metric. One computes things on sphere, and then there's a constant Cn. And if alpha equal to the positive part of this Q, dVg, if that's less than this Cn, so for example, C in this R2, C2 is 2 pi, and C4 now is 4 pi squared. So if it's strictly less than this, and if beta is equal to the negative part of G is finite. So together we have Q is integrable. Okay. But only the positive part is you have a constraint. Okay. Then you have an isoperimetric inequality for all omega in Rn. Okay. You have this omega, the G metric, the n minus 1 over n, the volume bounded by some constant n alpha beta is computed, but not too precisely. There exists some constant C depending only on alpha and beta and times omega G. This is for all omega in Rn. Okay. This G metric. Okay. So there's Q curvature. This Q curvature is size of it globally controlled is isoperimetric constant. The difference of this theorem to the theorem is here we only talk about the behavior at infinity. And here the omega is an arbitrary domain in the manifold, okay, in R4. So there's a global isoperimetric constant, which is controlled by this. So I wouldn't have time to sketch the proof of this, but let me say there is one key idea which is involved in proof of this. It's the only PDE one used is this simple-minded, this nth harmonic operator W, and then there's this geometric control. So one of the key idea which has introduced in this E1's proof is relate this behavior of Q in L1 and this PDE to the AP weight, the harmonic. In harmonic analysis, there is something called AP weight. Okay, and then what she did is relate this to AP weight. So let me say what is AP weight. Okay. So first, there is a theorem. So some idea in the proof. Key idea is to apply a result of David and Junet, David and Sams in the 1990s. Okay. And David and Sams are interested in weight K such that the isoperimetric inequality of the following type hold. We know isoperimetric constant is related dx less than equal to gradient f of x dx. This is the isoperimetric constant which holds on Euclidean space. This is the constant. This is the isoperimetric constant. Relate to isoperimetric constant for all f. And then what David and Sams do is they put a weight here, kx dx, and they are interested in what case this k, so I'm sorry, I should have n over n minus 1 on this side, and then this is on, say, Rn. And now they are interested in those weights such that there exists a constant such that is hold for all f, and then the weight here should be the weight k to the n minus 1 over n of x dx. So the question they are studying is, what are the conditions on the function k such that this Sobolev embedding result holds for all f? For all f. Okay? And the condition they put is if this k is what they call strong A infinity weight. Okay, then this inequality holds. Okay, and so, since this inequality really says that in a measure space kx dx, there is an isoperimetric inequality. So E1's key idea is to show e to the nw equal to k, and with the condition like that, this alpha beta is less than alpha n, then this would imply this is a strong A infinity weight. So that's the key step. Okay, so that's the key step. But now let me say what is a strong A infinity weight. So a strong A infinity weight, this paper of David and Sang is a very involved, very fine analysis, very long paper. So they introduced different way of measuring this weight, and here is their definition of A infinity weight. Okay. So given a weight k, they define a distance in k weight of xy, and this is what you think it is. This is in of all curve gamma joining x and y, and integration of k 1 over n and gamma s dx. So that's one distance function. Distance in k. Okay. And then they talk about another type of distance function. They call it del k of x and y. And del k of y is they begin to look at the ball centered at x plus y over 2. So given 2 points x and y, they look at the ball centered in the middle and of length x plus y over 2, and the length is x minus y over 2. They look at that ball, so this ball. And then they look at k of z dz to the 1 over nth power. Okay. So k is called strong A infinity weight. Wait, if these two are comparable, if this distance k is less than constant times del k and greater than some other constant del k. These two distances are measurable, are comparable. That's what they call strong A infinity weight. Okay. And it turns out this weight has a connection to many types of AP weight already studied in harmonic analysis. I will not go into detail, but the relation is A1 weight is containing AP weight and containing A infinity weight, and then strong A infinity weight is something which is greater than A infinity weight, but not may not be in AP. if you have not seen this before, please just forgive me. These are the harmonic analysis AP weights. Okay, this means some Holder inequality holds in this sense. A1 weight is relatively easy to define, and that's Hardy-Little maximum function using L1. So a function is in A1 if it's a maximum function is in L1. The key thing now is, let me say one of the key facts. It turns out Rn 1 over x to the power, say C power, okay. This is in A1 way if gamma is less than n and greater than 0. Okay, so there is this gamma is in this weight. Okay. And one of the key steps in the proof is if Q is in L1, then and G is normal metric. And one of the key steps in E1's theorem proof is he proves that this would imply e to the NW is in A1 weight if this alpha is less than the positive part, W plus. And W plus is defined to be, W is this 1 over 4 pi square integration and so on. And W plus is the same integration involving Q plus. This is QE for W. This is Q plus. Law 1. Okay, so it turns out that the measure of this is less than suitable measure correspond to in this expression. This function is in A1 way. Okay, and that's the. And then there are other much more complicated analysis involved. But one key fact to use is there is a measure involving the weight. Okay, and so this is, I hope I give you some feeling. At least, although this is such a simple definition in this simple case of Q curvature, the size of it gives you a lot of geometric information. Yeah, we